In this lab, we will take advantage of microcontrollers von Neumann architecture, which allows us to write some data in flash memory, which is permanent memory, so that when we turn off and on the microcontroller, it can read previous values of some variables from flash, not from RAM, so they are not lost, so they are restored. So basically what we're going to do is we're going to make a code which counts how many times we press a button on this board. And even if we turn off and on again the board, the value will be restored. It will be saved and restored. Generally, all variables that we create, they are created in random access memory or CPU registers. And after power outage, they are, the information is lost. They are set to 0 or something like that. So these variables, when we restart the processor, their values are not retained. So to retain the value of variables, we either have to store them in external memory like EEPROM or do something else. For example, in this processor, we can actually store them in the CPU main memory. In our microcontroller, for example, in a memory and bus system, if we check out our memory structure, then the Silicon Labs chips have a special location in flash memory called user data page. Its size is 1 page, and you can write some values into it. You can erase this page and write new values. And even if you reprogram the flash main block, the user data page is not erased. So for example, we have this code. I right click on the hex file and I want to flash it into the processor. Flash is overwritten, but user data page is separate and it's not overwritten by default. We can flash erase, select some region which is equal to the flash user data page and then flash it. But we don't usually do it by default. So let's start programming. So first thing that we need to do is we need to make some driver for button so that when I press the button, some counter is incremented or decremented. So let's do that. Let's create a new library, right click on the source file, folder and create new header file. We will call it buttons.h. And let's create buttons.c, new source file, buttons.c. In this buttons.c, hashtag include buttons.h, save. And in buttons.h, buttons are general purpose input output pins. So of course we have to hashtag include emgpio.h. All of these drivers should also include clock management unit and enable GPIO clock. But since I know that all of these libraries will use GPIOs, I just turn on GPIO peripheral clock in the main code in the very beginning before calling any other function. So GPIO clock is running by default in my case. So of course, we will need some function which will be void buttons init void, something that initializes buttons, turns on their pull-up resistors, attaches an interrupt to them, and so on. So buttons init is, of course, a necessary function here. So in order to initialize buttons, we will do the following thing. We need to set buttons as inputs and with pull-up resistor. We can also check out the development kit's schematic and see the way in which buttons are attached. In this case, we can see that actually the buttons have a pull-up resistor to power supply through 1 megaohm, and also they have 1 nanofarad capacitor for some noise cancellation and debounce. So actually we can just set them as input, and that's all. By default, all pins are inputs by default, so actually we don't even have to set the pins as inputs because that's the default value. If we go to reference manual, GPIO, registers, and mode, so by default, the value is disabled. So yeah, we should actually set it as input. So let's do that. Let's hashtag define button 0. I guess it's button 0 and button 1. Button 0 port, hashtag define button 0 pin, hashtag define button 1 port, hashtag define button 1 pin. And let's look at schematics, or in the kit's description. I guess it's in user guide, development kits, user guide, yada yada yada. Where is button information? Okay, it's right here. So buttons, button 0 and button 1, they are port B9 and port B10. And besides, port B10 can wake the processor up even from shutdown mode, which is deep, deep sleep. So port B9 and port B10. Okay, so in the code, I write button 0 port is GPIO port B, and also button 1 the same, and pin here is 9 and here is 10. Button 1 is port B10, button 0 is port B9. Now in the code I write GPIO pin mode set, button 0 port is the first argument, then which pin, button 0 pin, GPIO mode pull up input, and should we enable pull up or pull down? No, so it's 0. And I copy this line once more and change for button 1 port and button 1 pin. Okay, so now these buttons are enabled, so to speak. And since they have external pull-up resistors, we don't even have to use internal pull-up. Okay, so now let's check out how we can enable interrupts. So in for all of these pins, there's a special register. Let's see, register map. There should be something like interrupt enable register. Okay, here it is, GPIO interrupt enable. So basically with this register, we enable certain pin to have interrupt, and we will need to enable pin number 9 and pin number 10 interrupt. And then we also need to tell which port pin it is, because there's a limited amount of interrupts that we can have. The microcontroller has up to 200 pins, and we cannot have 200 different interrupts. So for these processors, we have two types of interrupts. One is for even pins, and the second is for odd pins. So you can have two different. If you have two buttons, for example, you would put one on odd and one on even pin number. So this is how you can distinguish between two pin interrupts. And the second is the pin itself can have a pin number interrupt, and you can understand which port, which pin it was. Just two pins, for example, in these microcontrollers cannot have the same number. So if you use port B pin 9, you cannot also use port A pin 9 for interrupts, because then microcontroller doesn't know which one it was. So you always need to check out the microcontroller's limitations for pin interrupts. I have also seen microcontrollers that only have interrupts on 2 pins, and that's all. You cannot set any other pin as interrupt. So be careful about that. So in this case, we can have up to 16 pins as separate interrupts. They will be grouped between odd and even pins. Just don't use 2 ports with the same pin number. Okay, and to enable an interrupt on a pin, let's see, port B mode. We are going to use an API from Silicon Labs, which is the following: GPIO int config. They have basically written an API so that it's easier to configure this thing. So we want to configure an interrupt. So if we want to enable pins interrupt, we need to tell which port we want to use, which pin, and whether we want rising edge, falling edge interrupts, and do we want to enable or disable them. So of course we will want to enable them. So let's write. So this is the port name, this is the pin name of our interrupt. And next is, do we want it to happen on rising edge? Usually no. Pins are usually configured in such a way that when you press it, it goes from high to low. So we don't want it to have an interrupt on rising edge. So you type false. And do we want it on falling edge? True. And do we want to enable it? Yes, true. So like this. This is for button 0, and for button 1, these 2 lines. This enables interrupts for GPIO locally. And then we have to, as usual, enable GPIO interrupts globally through nested vector interrupt controller, enable IRQ, and the name of the IRQ is GPIO. And as I said, there are 2 different interrupts, odd and even, for odd pin numbers and even pin numbers. So GPIO, even ERQN, and the same line for odd, because 10 is an even number and 9 is an odd number. So like this. By writing these things, we have turned on falling edge interrupt on each of the pins. So when I press it, special functions will be called. And the names of the functions are as follows. When we have button 0 pressed, it's 9, it's an odd number. So function called GPIO odd IRQ handler is called. If we didn't define this function, then compiler would not find it and either give us an compilation error, or on the interrupt, it would just see that there's no such function and go back to main code. Or maybe some other compiler would compile it in such a way that the code crashes. So if you enable an interrupt, you have to write this implementation of this function, just using this special name. So when we press the button, we want to, first of all, clear the interrupt, GPIO int clear, so that, we don't have this error all the time. And how to clear this interrupt, we could use GPIO int get. But the problem is that if we have odd and even interrupts at the same time, probably it will return both and we will accidentally clear both of them. So the best thing to do is this. If we know that we only have enabled interrupt on pin 9, then we only want to clear bit 9 in the interrupt register. So int clear 1 shifted by 9, or better yet, without magic numbers, 1 shifted by button 0 pin. So in this way, we only clear the interrupt that was called by button 9, button 0 pin 9 instead of button 1 pin 10. Okay, next thing that we can do is, for example, for debugging purposes, printf button 0 was pressed, new line, so that we see that something is happening. And basically that's all. And let's write identical function for the other button, the button number 1. It's pin number 10, so it's even. ERQ handler, this is the name of the function, and then we want to clear only bit number 10 in this register and change to button 1 was pressed. Okay, so this code should work to configure both interrupts, and when one button is pressed, one interrupt is called, and the second button is pressed, the second interrupt is called. If you had more pins with interrupts in each of the handlers, you would have to go through every pin and check whether this was the pin that caused the interrupt. Okay, so having 2 buttons is pretty easy here. Okay, so let's save all. This is button C, this is buttons.h. In main code, we need to hashtag include buttons.h. And in the main code somewhere, we need to, usually after print init, because our code prints text, so the print should better be initialized. So somewhere here, we are going to call buttons init, and that's it. So whenever we press the button, an interrupt will be called. So let's build it. Let's flash it. And I am now pressing the button. I hope it works. Okay, button 0 was pressed, and I pressed button number 0. So it works. And button 1 was pressed, also works. Okay, now let us create such code that there's some counter which tells us how many times we have pressed the button. In this case, we will use, in button C, we will use a somewhat local global variable, actually 2 variables. So I don't know, for example, unsigned 32-bit integer button 0 press counter, and button 1 press counter. As I said, you don't have to initialize them to 0 because the startup code automatically initializes global variables to 0. Automatically initialized to 0. So, and then when we press, for example, button 0, we want to increment this button 0 counter ++, and we will also print out button 0 was pressed %u times. %u is for unsigned integers, so we want to use this, comma, button 0 press counter. And for even ERQ handler, button 0, or button 1 press counter also increments on each button press. And also here, I just copy this code. Button 1 press counter times. Okay, so let's build it. Let's flash it. And let's see what happens. So I press the button number 0, and as you can see, it counts how many times I have pressed this button. Okay, so 46 times. And then the other button press counter counts the other number. So now 17, 18, and so on. However, if I switch off the development kit, I switch it off with this switch. You can, just set it to the left position. And when I turn on this device again, if I press the button, it starts from 0 because these variables are initialized to 0 automatically. And even if they weren't, if I unplug electricity, then all of these variables lose the value. So what we want to do is we want to write some code with which we store the button press counter value into flash memory so that the device remembers how many times we press the button. So let's do it as a training example. And, let's create a new library, and we will call it flash mem, with which we will write the values to flash memory. So on the source folder, right-click, new header file, flash mem.h, and new, oops, what happened? New, whoops, new source file, flash mem.c. In flash mem.c hashtag include flash mem.h. And to use flash memory for reading and writing, we need to include a library from Silicon Labs called Memory System Controller. It's also a peripheral. It's realized as a peripheral, and its name is MSC, Memory System Controller. And this library basically has an API with which we can erase flash memory pages and write some data to them. We cannot just simply write into flash memory. It doesn't work that way because it is read-only. There's a special sequence with which the microcontroller can write into flash, and so we need to use a special function because what we write into flash will be burned into the flash, so to speak. So in mlib, right-click on this, for example, ADC, browse files here, and what you need is MSC, Memory System Controller, MSC. Just drag and drop in mlib. Like this. And we have MSC here. And in flash mem, we write hashtag include MSC or mscs.h. Save. And there's some info. Okay, so we will want to write the following API functions in this library. We will call, first of all, initialization. Maybe there's some sequence with which we initialize the memory system controller so that it's able to read and write some data into flash. So let's write it this way: void flash mem init, and void. And also we will want two APIs, void write, well, for example, write counter, sorry, write counter1 to flash, and the counter value and the second API write counter 0 to flash, and counter value, and two more APIs will be unsigned 32-bit integer read counter 0 from flash, and the same name for counter 1. Of course, this is not, perfect way to do it. We could write one function which writes both of them, but this is just an example. So we have option to write counter 0 to flash, write counter 1 to flash, read counter 0 from flash, read counter 1 from flash. So let's write implementation of all of these functions. Flash mem init. So to initialize flash memory, we can go to mlib documentation, and in mlib library, and there is this memory system controller somewhere here. And basically, yeah. Here's even an example code, but we need to call MSC init. So memory system controller has the following API. We can initialize it. We can write word. We can mass erase entire flash memory. Yeah, or write by words. So to initialize the flash memory, we need to call MSC init. So I just type MSC init. So this initializes memory system controller so that writing to flash memory is enabled. Next up is write counter 0 to flash. And write counter 1 to flash. Also read counter from flash and read counter 1 from flash. So we just need to decide as the system architects how we're going to store these values. Also, I need to mention that this memory is organized in 32 bits wide, so we cannot write one single byte into flash memory. We need to round up the sizes of our variables to multiples of 32 bits because the flash memory is organized in 32-bit width, so we can only write 32-bit numbers in it. So this is why the counters are 32-bit wide, so everything is fine. You just have to know that you cannot write, for example, 1 byte into flash memory. You need to write 4 bytes. If the variable is just 1 byte, then you add zeros in front of it. Okay, so we have this flash user data page. And here's a small example how to use it. Basically, we create a pointer to the beginning of the user data page. So I just copy it from the example. So this is pointer to unsigned 32-bit integer, and its location is the same as the beginning of user data location. So user database starts at this address, and we just create a pointer which points to it. And this type of this pointer is basically, you can imagine it as a pointer which points to 32-bit variables, or as the beginning of 32-bit variable array. Okay, so user data page variable is at the same time pointer to 32-bit variables, or an array to such variables. C programming language will allow us to use it in a very nice way. So let's use the paint again. User data page is a page which can store 32-bit variables. And it has many memory locations. And user data page variable simply points to the first one of these places. It points to the beginning. So the simplest way that we can do is just we write counter 0 on this address and counter 1 to the next address. And the cool thing in C programming language is that we can just use square brackets and 0 or 1 because they work on pointers just the same way as on arrays. And this way we can access the 0th location or the first location of this data page. So here we will have counter 0, and here we will have counter 1. Okay, so when we want to write counter 0 to flash, well, what we can do is we can use MSC write word. So we need to check out one of these write word functions is fast, but it disables interrupts. Well, actually, it's good, but it depends on interrupts. However, since we want to call this function from button press interrupt, we should not use this function because it uses interrupts itself, and button press has already paused all interrupts, so this probably will not work. We need to use this MSC write word slow version. Writes data to flash memory, but this function is interrupt safe. Okay, so let's do it. MSC write word accepts the following arguments: pointer to the address in the flash memory where we want to write the information. So basically it's user data page element number 0 address. So I type address of in front, it's ampersand sign shift +7. Address of user data page element number 0. And as I showed you here, element number 0 is here. Basically the same value that the pointer is pointing to. And element number 1 is just the next 32-bit address and location in the flash memory. So it's something like this. Write word fast. This is the address. Then we need to give pointer to data. So it will be just address of counter value. It's all done through pointers, so we need to give address of counter value. And how many bytes? Well, 32-bit number is 4 bytes long, so I just type 4, and that's all. However, before we write to the flash memory, we also need to erase the previous value, because flash memory can only be written from ones to zeros, and after writing, if we want to write a new number, we have to erase the previous contents. So there's no other way than to just call function MSC erase page, and the page that we want to erase basically is the user data page, all of this page. So we can give the pointer to this thing. So we erase all of the user data page, the old counter value, and then we flash the new counter value into the flash. And now let's copy this to the second counter, counter 1, write counter 1 to flash. So here we erase the previous values, and then we write a user data page into the first, not not the index 0, but index 1 of user data page. So we tell them to write the value into this location with offset 1. And this argument counter value, we just give address of counter value and 4 bytes to be written. Okay, so let's see. Write word fast, pretty easy. And how to read counter 0 from flash, basically we just ask, return user data page element number 0. And to return counter 1 value, return element number 1. So like this. And in our buttons program, basically, when we initialize the buttons, we want to restore the value of button press counter into the variable. So I type button 0 press counter equals to read counter 0 from flash. For it to work, I need to include flash mem into the buttons.h file, and button 1 press counter is read counter 1 from flash. Okay, and every time we press the button, we increment the counter, but we also need to save the counter into the flash memory. So we need to call write counter 0 to flash and give the button 0 press counter value, and then print it out. And for this thing, we need to give write counter 1 to flash and button 1 press counter value. And in the main code, we need to also hashtag include flash mem library, and after initialize or before initialization of buttons in it, we need to initialize flash mem. Okay, so now we initialize a memory system controller, then we enable buttons interrupts, but also we read the last button press counter values from flash memory. And every time we press the button, previous value is erased and new value is written into the flash memory. So let's build it. Let's see if it works. Okay, let's see. Let's flash it and see how it works. Flash to device, program, clear. Okay. Now I press the button. Interesting. Okay, so button 1. I'm pressing button 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 many times. Now I switch it off. Now I switch it on and I press button 1 again. And as you can see, it started counting from 19, from 24, 27, okay, 35, 36. I switch it off. I switch it back on. I start to press button and it continues from where it was. So as you can see, this thing works. It stores the flash, the counter value into flash, and then when the program restarts, it reads the last written value. Now let's press button 0, but button 0 started from 0, that's good. Now I switch it off, I switch it on, I press it and it continues from 9. I press button 1, oopsie, there's a mistake in our code. That when we write one number, the second one is actually erased. Check it out. Well, I made this mistake deliberately so that you would notice it. When we write one of the counters, we erase the entire page. Also, in the same page, the second counter is written. So basically, what we do is when we write one of them, we erase everything, and then we write one counter. When the other button is pressed, we erase everything, including the first counter, and write the second counter in Flash. So it's wrong. So what we would need to do is one of two things. Either put each of the counters in its own separate page. So when we erase one page, the other one doesn't care. But unfortunately, the user data page is only one page, so we have to fit both variables in the same page. So what we actually need to do is when we write, want to write counter 0, we need to first retrieve counter 1 value and only then write both counters into the flash memory. So we need to make some temporary buffer with two elements. So in buffer address 0, we want to write the counter value. And in buffer element number 1, we want to write the other counter's value, which is located in user data page index number 1. Then we erase the entire page, and then we want to write into user data page. So I'm removing these things. Not just one of the counter values, but both of the counter values. So we give the buffer which contains both of these values in the correct order. So it takes counter number 0 value, also counter number 1 value, which is retrieved from the flash a step before, and then writes both of them. And the number of bytes that we want to write is 8. And now we will do the same thing for the other counter. Maybe I'll type it down again. So we create a buffer where we want to store both current counter value and the other counter's value. In the 0th location, we read from flash and temporarily save the counter number 0. And in location number 1, we store the new counter number 1 value. And then we erase the page, and then we write into user data page the buffer, both values of buffer. So it's 8 bytes. And now we can build it, and now it should work correctly. Okay, so I take this thing and I press the button number 0 10 times, and I press button number 1 5 times. Now I switch this thing off. Now I switch it on. And when I press button number 0, it says 11 times, so it restored the 10, and button 1 restored 6. Button 0 20 times, button 1, let's say 15 times. I switch the device off, I switch it on, and now button 1 16 times and button 0 21 times. So now the code works correctly because we cannot, when writing one of the variables, we shouldn't delete the other one, erase the other one. Okay, and now the last thing that we need to talk about is flash where. So the microcontroller's datasheet clearly states in something like electrical characteristics, flash. The flash can only survive up to 20,000 erase cycles. So if you put it as a door opening counter in some busy pub, then people are maybe opening and closing the door hundreds of times per day. So this thing would become useless after just 200 days. So since all flash memories wear out during the erase process, especially erase process, we want to save the flash memory from such wear. And so this simple code works, but usually people implement some kind of wear leveling algorithm that, for example, you write counter numbers at locations 0 and 1, and next time you write them in locations 2 and 3, and then to 4 and 5, and then to 6 and 7, and so on. And only when you fill this entire flash page up to the maximum, you erase it entirely and start from bottom again. If you want to know the flash page size, one flash page size in this microcontroller is, let's see, flash page size. It is, I think it's 2 kilobytes, but it should be written somewhere here. Flash page size. Okay, flash size is here, and flash page size for this processor is 2 kilobytes. So it's 2048 bytes divided by 8 bytes for two counters, each having 4 bytes. You could write 256 times into the flash memory and only then erase. If you implemented some kind of algorithm where you only write until the flash page is full and only then erase. So it's 256 times less frequently done process, so the flash memory would wear off much slower. And of course, all modern operating systems and computers implement some flash wear leveling and so on. So, normally you would upgrade this code in such way that you would have flash wear leveling. So your job is to write down this code, compile it, test it out that it works, and then you upload it in Ortus. So let's recap one more time. In order to use memory system controller, we had to add a memory system controller API library. We need to call memory system control init, and it initializes it for writing. To erase a page, we simply call MSC erase page, and we give the pointer to the beginning of that page. For example, user data page pointer. And to write, we use MSC write word. We can only write 32-bit variables. We give the address in flash memory to which we want to write, the start address. Then we give the data that we want to write in format of 32-bit integer buffer. And then we tell how many bytes we want to write, but it has to be multiples of 4, 4, 8, 12, 16, and so on. You cannot write 3 bytes. And to read from flash, you just read like from any other location in memory. This pointer points to user data page beginning. So at the first 32-bit location, we have the counter number 0, and at the next location, counter number 1. So, and for buttons, we just initialize buttons to call interrupt functions, and inside interrupt functions, we clear the interrupts, increment the counters, write them to flash in such a way that the other counter is not deleted, and print out a message. So this is how the code looks, and also this is the main code. So in main code, we added flash mem init and buttons init, and we both put buttons init after we have initialized flash memory, and also after we have initialized print, just in case you press button, then the print function is operational. And that's basically all in this lab. So this is the main code. You can pause it and type it down. This is buttons.h. This is buttons.c. This is flashmem.h. And this is flashmem.c. So good luck typing it all.